Hello, we are Solar-SPAR. Solar-SPAR stands for Solar Sail Propulsion for Alternate Redirection.
Hi, I am Alec Moni, and I am the team lead, as well as the power communications and electronics lead.
Hi, I'm Shay Henley. I'm the Astrodynamics, Instruments, and Solar Sail Module lead.
Hi, I'm Jackson Barger. I'm the Propulsion, Simulation, and Software lead.
Hello, my name is Samantha Stevens, and I'm the Systems and Integration lead.
Hi, I'm Christian LeClaire, and I'm the Structures lead.
For centuries, large square sails moved ships across the ocean. They moved slowly and were restricted to the direction of the prevailing wind. Triangular airfoil-shaped sails revolutionized travel across the seas, allowing for faster speeds, tacking into the wind, and opening new routes. Just as triangular sails transformed seafaring, our vision for the next generation of solar sail satellites will exponentially increase the operational domain and use case of solar sails as a primary propulsion system for satellites.
The main principle that allows solar sails to be useful as a propulsion method is the conservation of momentum in quantum mechanics. Photons do not have any mass, but as proven by the de Broglie relation, they have momentum. Each photon has a very small amount of momentum, but the cumulative effect of the light reflecting off of a large sail creates a small but usable propulsive force. The force on the solar sail is dependent on the solar flux, the size of the sail, the angle of incidence with respect to the solar flux, and the optical properties of the sail. The three solar radiation pressure models were first validated against each other over a range of angles of incidence and sail areas, all showing good agreement. Next, the models were validated by replicating a published thrust envelope of the LightSail 2 spacecraft. This also showed good agreement and gave us confidence in our model to start sizing the solar sail. The driving constraint to sizing the solar sail is the time requirement to spin up to 1 revolution per second in 6 months. The 6-month timeline is further reduced by the Earth blocking the sunlight from reaching the solar sail during parts of the orbit. Orbital simulations calculated the satellite to be in sunlight for 15 hours per day in orbit. The fixed timeline requires a constant average angular acceleration to reach the desired angular velocity. The angular acceleration requirement can be related to the moment created by the solar radiation pressure and the dimensions of the CubeSat using Newton's second law in its angular. The sail area was calculated to be 3 meters squared, and a factor of safety of 5 was introduced, leaving us with a final sail area of 15 meters squared.
The goal for this project was to find a way to use solar sail propulsion to redirect an orbiting object into a new path that would not be limited by the direction of the incoming solar flux from the sun. To accomplish this goal, our idea is to store kinetic energy in the CubeSat assembly by increasing rotational velocity. This energy can then be used to redirect the secondary payload. Our 5-year mission begins with a launch into low Earth orbit. The CubeSat is jettisoned from the launch vehicle into a 750-kilometer circular orbit where the rest of our mission takes place. Sail controls are required to create a moment in only one direction, so we developed a mechanical approach to control the direction of the rotation by angling the sail either perpendicular or parallel to the incoming solar flux. This essentially switches the force of the sail on and off. For the first 180 degrees of the CubeSat's rotation, the sail normal is oriented parallel to the solar flux to maximize the moment in the direction of spin. In the second half of the rotation, the sail normal is rotated perpendicular to the solar flux to minimize the moment in the opposite direction. After the 1 revolution per second goal is met, the secondary payload is released from the extension arm into a new orbit with a delta V of 10 meters per second. After the secondary payload is launched, the satellite begins to de-spin and de-orbit operations to comply with the FCC requirements.
Missions for CubeSats of this size cost upwards of a few $1,000,000, so we had to come up with a prototype design that didn't involve building an actual CubeSat. Our group decided to build a scale model using 3D printed material to demonstrate the deployment and test the control system operations of the CubeSat to keep everything within our budget. The control system for this prototype involves a rotation of the sail based on its angular position, just like the real CubeSat would if it was built. The main components of the prototype are the extension arm and operating motor, sail deployment device and its driving motor, the sail rotation motor, and the base. An Arduino software program controls all the DC motors in the prototype and reads the angular position from a 9 degrees of freedom sensor. The sensor is in a feedback control loop with a DC motor that rotates the sail, so the correct sail orientation is maintained throughout the full rotation. 3D printed materials were used to create the CubeSat structure and the housing for internal components that would allow for a low-cost and highly iterative design process. The extension arm, since it wasn't vital that we built it ourselves for this project, we decided to buy a kit online to make the assembly process much easier. Each component was benchtop tested individually and again at the subsystem level before bringing all the pieces together as a whole to ensure all parts worked as intended. The base will have an external motor in it separate from the CubeSat that will be used to spin the prototype to imitate its rotation in space, since we can't rely on forces from solar flux to overcome the atmospheric drag and friction on Earth. The connection between the base and the CubeSat structure utilizes a ball bearing in order to reduce the friction presented when spinning the CubeSat.
The sail deployment device is made up of 4 retractable booms that support a Mylar sail. The solar sail is packaged into the sail deployment module in 4 quadrants, which get extended when the booms deploy. One of the challenges we experience is that our metal booms are not structurally stable enough on their own to stay in place. The Lightsail 2 team utilized a specialized metal alloy laser welded together. We created our own version of these stable booms by using epoxy, but it cracks when it's folded. So we'll demonstrate sail deployment separately and then use our stable, unfoldable booms to hold the sail when the spacecraft model is spinning. Another issue we ran into was the folding of the Mylar. The folding was significantly more difficult than anticipated due to the complex folding pattern required to fit in a small volume. The strict volume constraints of the project stemmed from the need to fit within a commercial CubeSat frame.
Solar-SPAR's innovative concept expands solar sail satellite use cases to include new operational domains and mission goals, including orbit maintenance of small satellites and cleaning up space debris. Space debris is an increasingly important issue that negatively affects the ever-growing space industry and is a hazard to all satellites and space missions. Spacecraft utilizing sails like our Solar-SPAR design could be used to continually deorbit space debris without adding to the problem. Additionally, spacecraft with the ability to deploy and move a solar sail could use this technology as an attitude determination and control system. Solar-SPAR marks the beginning of a new era in solar sail space travel.